Hi, it's Robin. I've got here Commodore's Datassette. They went through many variations of this from the introduction of the Commodore PET and continued making them for the VIC-20, Commodore 64, Plus4, C16 era, and they were even available and worked on the Commodore 128. Not that I think all that many people used the Datassette with their Commodore 128, but what do I know? But they all basically work the same principles, even the same connector, except in the case of the Plus4, the 264 family, which had a DIN connector. The Commodore Datassette had some nice advantages over a lot of their competitors. Some computers didn't even have an official tape deck. Oh, big. So certainly some people would just use a more regular tape deck. I've got this old Supersonic, not that this would be the only one, but when you bought a personal computer back in the late 70s or early 80s, you might just use whatever tape deck was already in the family. Now, of course, that has the advantage of you already have it, you don't have to pay for a new one, but it actually has several disadvantages. The Commodore Datassette just had one cable, one connector, and while proprietary is often like an evil word, this was actually pretty nice having all the cassette signals available right here on this one cable, including power. So it really was just single plug and play. By the way, most or all datasets have this ground cable that comes off the side here, and it's a throwback to the PET days where you're supposed to ground. There's a little end connector here that you were supposed to screw onto your Commodore PET for grounding, but actually just got in the way for the later computers, but they kept keeping it there for PET compatibility. I guess that was nice of them, but that's why a lot of users just taped it away. I think I taped this away. That's decades old tape on there. Just in case you're wondering what that's about. Okay, but compare that to this tape deck. Now, of course, it's nice that this tape deck has so many features. It's got all the different plugins on this side, at the front, controls here and here, volume and tone. Lots of features, lots of options, but when you're dealing with cassette data, that's actually a drawback. Every variable you introduce, like a tone control, a volume control, just introduces more variables to the data cassette. It's actually audio, it's still analog, but the computer interprets it as a digital signal. All those variables affect the sound, and some tape decks even had automatic volume control. All those things could actually reduce reliability instead of improve it. Oh, this is heavy. Those are external speakers. Actually, I guess those powered on this one. And microphone for input and a remote jack. These would be 3.5 millimeters, and that remote one's usually 2.5 millimeter. So actually you might end up having to use the line output. I didn't even mention the fact that a stereo deck, that data is usually recorded in mono, and a stereo deck can have some negative effects on that too. And it requires external power. Somewhat better is this Mattel Electronics Aquarius data recorder. So it's a tape deck, dedicated to data, and people might scoff at that, but that actually means it's mono, that it has fixed volume and tone settings, which means there's no variable there. You can see it actually greatly simplifies the controls. Actually improves the odds of you successfully loading or saving with a deck like this, all other things being equal. But even this dedicated deck still has a separate power cord, and it has independent ear and mic. Oh, actually had those reversed, not that the color actually matters. But 3.5 mil jacks for the earphone and the microphone, output and input. And then it has a 2.5 millimeter jack for the remote. And what that allows is a computer that also has a remote jack on it. It allows the tape deck to be paused or played under computer control, which can be handy for loading a multi-part program and other purposes. So still even a dedicated data deck. You got up to 4 chords. I should mention that the Datassette was always very competitively priced, so you wouldn't find the Aquarius deck probably any cheaper, and certainly a high-quality standalone tape deck wouldn't have been lower cost either. Although I suppose at least you could play music cassettes on it too. So I grew up with one of these. Even though I lived in North America, I did have a Datassette on my Commodore 64. It's just a myth that nobody in North America, USA, or Canada used tape with their personal computers. Any of us who got into computers from the late 70s to the early 80s certainly did use tape, but then diskette really took over, and due to various economic concerns and so on, most of us had transitioned to disk by, say, 1983, 84, and on, while in certain other parts of the world, especially the UK, the cassette lived on, especially on the Commodore 64 scene. But we had at least a couple years of good cassette use on the C64 in North America. And you could buy tapes in the store and so on. I did a whole video about that. So I want to talk a bit about how the Commodore 64 and the Datassette work with each other. And it's actually a bit more complicated than I thought. There's more to it. And I actually learned quite a bit as I studied this in the last week or so. So I'm going to show you a few things, and hopefully some of it's new to you too, or at least it'll help you understand better how it works. Okay, so I've got my PAL C64. This is actually my Swedish C64, thanks to my friend Mager Valp again. I'll be using it for at least part of the demonstration here today, just because. Nice to see a bread bin. Got here a game on tape, Road Toad, which is actually made here in Canada originally, but this is the European PAL release. So we already discussed that the power comes from the C64 into the tape deck, and as you might expect, you want to fast forward your tape, or rewind your tape. And that works as you might expect. Doesn't seem like a surprise. And of course you can even press play and the tape will start moving. And I don't want to press record. Well, I think it's probably record protected anyway. But if this tape was write enabled, then I'd be able to press record as well. And that's all independent of typing load or run or anything like that. A user, of course, may want to fast forward or rewind their tape, and that you do that as you expect. There's actually more going on with that than you might think. And this was the surprise to me. Now here's one sign of that. If I'm fast forwarding a tape, and I tape sys 64738, okay, the fast forwarding paused. If you couldn't see it, you could probably hear it. That by doing a sys 64738, that's a reset command. I'll just do rewind again. Actually stops rewinding for a little while. Or for that matter, again, I'm fast forwarding. I press this reset button I have here on the EX3 expander. Exactly the same thing, and that's a hint that the cassette deck is actually at least partly under computer control. Normally the way it responds so quickly to fast forward and rewind makes you think that you have direct control over the tape deck, as if you are the master here. And actually that's not true. The computer ultimately has control over that. So for some other examples of the Datassette not working always the way you might expect, I've got here the last V8. I've got a cassette version here. It's one of my favorite games. So I actually looked through many cassette games until I found one good example of each thing I want to show. And I load them from cassette, but then I use the Super Snapshot on, well, I was using the Kung Fu Flash, but with the Super Snapshot ROM to take a snapshot or freeze it. I'm going to be loading it from disk today for two purposes. One is just to save all the time so that we're not sitting here waiting for a bunch of games to load from cassette as examples. But the other one is to show that the effect is at least somewhat independent of whether you actually loaded from cassette or not. It's actually a software thing. Okay, so here I've got a directory full of these games. So we'll look at the last V8 first. Again, This is a snapshot I made using my Super Snapshot cartridge. Okay. I can't help myself. Gotta play one game, right? Such a tricky game. I know a lot of people hate this game, but oh, I love it. Oh, I gotta practice more. It's really weird because it's not like turn left or right. It's you push in the direction you want to go. Oh. Great music by Rob Hubbard. Great graphics, I think. I love the scenario. I actually find the gameplay pretty fun. Real challenge. What? Oh. Wow. Yes, yes, yes. Woo! First try. So yeah, that's game over. Okay, so anyway, the reason why I load this up is because it disables the cassette deck. Look at this. Press fast forward, nothing. Press rewind, nothing. Play, nothing. And hopefully you notice how quiet it is. I guess that's a minor annoyance for Last V8. So I'm initially recording this. It's around Halloween, so I thought loading up Cauldron 1 or 2 would be appropriate. Okay, so we'll try Cauldron 2. Again, this is just a selection to show a few different possibilities. Okay, so here's Cauldron 2. These games are brutally difficult. So you're this bouncy pumpkin. Huge map, or at least it feels huge. Ah, 19. Well, if I can get that. There we go, I got extra. Oh, ah! This is pretty cool though, because the cackling, which is, you actually end up down in the first game, or at least the world looks the same as the first game. So that's pretty cool, the original Cauldron. Oh, there. Fell right out of the castle. Okay, anyway. Sorry, I can't help myself playing a bit. Now, in this game, this is true of Cauldron 1 as well, this game actually allows me rewind. Then fast forward and so on and play. But the difference is here, I hope you can hear that. There's a humming. I don't know if you're going to be able to see that. But basically this, called the capstan there, that's actually spinning. And it's spinning all the time. Put that back in. Here, let's put it near the microphone. Okay, so this game is allowing cassette controls. The motor is spinning all the time. If it wasn't obvious before when we were in BASIC, we could actually control the fast forward and rewind, but that humming wasn't there. This was always kind of present in my C64 experience, that sometimes the cassette controls wouldn't work, sometimes they would, but there would be a hum. But I never really consciously thought of it really clearly. I might be annoyed that I couldn't rewind when I wanted to, I didn't really think about this hum in the background, but now I think about it, you know, it was there a lot of the time. And just for one last example, here's that road toad I was talking about. Short little game. Okay, and it's just an okay Frogger clone. Very early game though, probably, I think it was actually from 1982. Published by the same company as that Frantic Freddy we looked at a while ago. But the point here is that fast forward and rewind work, and there's no hum. It's completely silent, just like in BASIC. I should mention one other game here. This is Lazer Force. Really tough shoot 'em up. Right. It's crazy difficult. Technically really impressive though. Oh, I'm not usually this bad at it. Can beat a couple. Oh boy. Anyway, I highly recommend checking out Lazer Force if you're into really tough shooters. Oh boy. Well, yeah, then the second phase is like the centipede sort of clone. Okay. There we go. Game over. Okay, so the reason I bring this up is I had actually asked on X-Twitter for games that do strange things with the tape motor. The very knowledgeable Warren Pilkington pointed out this game Lazer Force. And it has this strange option down here at the bottom, tape motor. So if I hold down the tape motor button and press fast forward, it actually starts moving. But here's a really weird thing. When I booted from cassette, this actually worked more normally. It did a full fast forward. It's actually doing this really weird staggered thing here. Almost like it's pulsing the tape motor on and off. So that's kind of its own mystery. And I'm not going to get into that now. But the point is that there is this option. I guess this was kind of a compromise between leaving the motor running all the time and allowing the user to have some control over the tape motor. If they want to fast forward or rewind, they could choose this tape motor option. Kind of interesting. I don't think that was very common. I think Warren said another game also by the same author. Was it BMX? I'm sorry I didn't make note of it. It sounded like BMX Simulator or something like that. A while ago, I did a Commodore 128 video about the C64 mode and the compatibility issues that it has. They're not serious, but they were interesting. And one of them is how location 1 behaves differently. And I had just written a very short program. I think it might have just been here, like print peak location 1. And then just for ultimate speed, I did a go-to with no line number, because you can do that for line 0, and ran it. And it prints out value 55 over and over again. Then what I did was I played around with the fast forward, rewind, or play. Maybe it was play and stop. Let's try that a few times. Rewind, stop. And some odd numbers occasionally showed up there, but you know what? It's going to be easier if instead I put a semicolon here, because then we won't lose so much on the, we'll see a lot more results on the screen this way, even if they're not formatted so nice. So here, I'll run it. Let's look at that. Okay, so there's a good one. So you see that the default value is 55. I'm just going to scroll this up here. So here, 55 is the regular value of peak 1 when you're not pressing any buttons. I'll just do that again here. When you're not pressing any buttons on the dataset, then it returns 55. And when you press the buttons, you get 7. And I'll explain what those mean in a bit. But viewer dark mo noticed that sometimes there was an intermediate value here just for a single print. You got 55 and 7. Here you have this value 39. And here you have a value 23 when you're going back from 7 to 55. So there's actually 4 different values. But as we see, normally it's 55. And when you're actively fast forwarding or rewinding or pressing play, then you get a 7. Here, I can even just like press play here, just to show that. If I peek it, you get 7. Or for that matter, if I'm rewinding, there, you get 7. I press stop, and now we have 55 again. But what is up with these intermediate values here, 39 and 23? Okay, so location 1 is the input-output port on the 6510 processor in the C64. And it has 8 bits. I'll group them in 4. And we number those bits 654 and 3210. That's the convention. But on the 6510, those upper 2 bits aren't used. They always return 0, and they're not connected to anything. It's actually a little odd that they return 0, because most disconnected lines actually return a 1. But anyway, these ones return 0. So there's 6 other bits remaining. Well, I should mention on the Commodore 128, it has an 8502 processor, and it has 1 extra bit. This bit 6 here is connected to the caps lock key, and we discussed that in that C128 video. So if the caps lock key is depressed, pressed down, or enabled, it returns a 0. Actually, the rest of the time it returns a 1. That's a potential source of compatibility issues on the C64 mode on the 128, because that bit is available even in C64 mode, returning a 1 if you don't press the caps lock key. But in reality, there's very few programs that seems to actually cause a problem for. Okay, and to look at the other ones, these 3 bits here all control memory, and we've looked at that in other videos, so we won't be talking about that now, but by default, they are all 111. This allows you to configure the memory map of the C64. There's actually about 88 kilobytes addressable in a C64, but only 64K of memory space, so the ROM is stacked on top. This bit would allow you to switch the basic ROM out, and the kernel ROM, and the I/O space, and actually different combinations of them. It isn't as simple as it says in the programmer's reference guide. These combine to 8 different memory mapping modes. And I've talked about those in other videos, and maybe I'll look at in more detail in a future one. But what we're interested in is these 3 remaining bits. And this one you might call the signal bit, and that's actually where the data from the cassette deck, or to the cassette deck, but we're not even going to be talking about that one today very much, but it does default to 0. And these 2 remaining bits are the real subject of today. And this one here is the buttons bit, and it defaults to 1 when no buttons are pressed, and it's 0 if any of these buttons or keys are pressed. And it's this group of 4 at the left here: fast forward, rewind, play, or record. Stop and eject are purely mechanical within the tape deck, but stop can sometimes be inferred when it follows one of these keys. So we'll be looking at that more in a bit. So yeah, basically all 4 of these share that 1 button bit. The Commodore can't tell the difference between you pressing any of these buttons. Did I show that before? If you just type load and press return, it says press play on tape. But the thing is, you can fool it. Look, I could press rewind instead. And hey, it thought I pressed play. Press stop. I'm going to erase that. Okay, and the final one here is M, the motor bit. And when that is set to 1, the Datassette motor is off. And if it's set to 0, the motor is on. but it defaults to 1. Okay, so now we can see where this 55 comes from. If this is the default value here, then these bits are worth, each one is like, this is 2 to the power of 0, or worth 1 in binary. 2 to the power of 1 is 2. 2 to the power of 2 is 4. So these 3 bits together equal 7. This bit is 2 to the 4, also known as 16. And this one is worth 2 to the 5, that is 32. So you add those together, and sure enough, you get 55. This is just binary to decimal translation. If you don't understand it, grab a calculator. Even the one built into your modern computer should do binary to decimal and hexadecimal conversion. Okay, so where does the 7 come from? Well, as we were discussing, if we change both of these to 0, 0, meaning that a key is pressed and the motor is on, then of course we just get rid of the 16 and 32. The 16 and 32 are no longer there, so we just have 7. I don't even need to print that, do I? Because all we're seeing are the 3 bits that have nothing to do with the tape deck. These are the 3 bits that control memory mapping. So now you might be able to figure out where we get 39 and 23 from, these odd combinations. Well, it's simply 7 plus 16 is 23. So that would mean if we had a 1 bit there, but a 0 bit here, and conversely, or opposite, if we have a 1 bit here, then we would have 7 plus 32, or 39. So those odd values up above happen when, for a moment, only one of these 2 bits is set. So I think we can examine this a little closer with the help of this little basic program that I wrote. Now, that cursor flashing is actually part of the system interrupt, and it's driven by CIA number 1, timer A, PAL, or NTSC. It does not matter. The system interrupt happens very close to 60 times a second. It's not driven by the time of day clock. It's not driven by the 50-60 hertz line. It is driven just by timer A in the input-output chip, and it's counting microprocessor clock cycles. Both PAL and NTSC C64s run at very close to 1 megahertz, that is 1 million cycles a second. And if you divide that by 60, you would have an interrupt occur every 16,667, say. You can't do fractional cycles. In reality, it's a little bit off that. The C64 ROM actually adjusts based on that. Okay, but the point here is this timer A high byte right here is 36325, and that gives us the coarse control over how often that interrupt happens. It's a 16-bit timer, so we could set the timer to happen everywhere from every 0 cycles, which is a very bad idea. It would never get anything done, or maybe every 1 cycle, all the way up to a maximum of every 65535 cycles, which would be the slowest possible 16 bits. So let's just try that. Poke 56325. So if we poke it with 255, now watch that cursor. You see how much slower it's blinking than normal. And it's just a little bit laggy now when we type. Not terrible. You see how much slower that cursor's running. Now if I add that 0 print peak 1 in, and now if I press play, stop, rewind. So much slower my cursor moves now. So you see how we got a whole bunch of 23s here now. And that's a clue that actually what is happening is the kernel interrupt is monitoring the key presses and it's engaging the motor. So you might think that you are fast forwarding or rewinding, but actually it's up to the computer. You press fast forward or rewind the computer will monitor that key press, and when it feels like it, it will engage the motor and actually allow the fast forward or rewind to happen. But back to my program here. That's annoying. Okay, I hit stop restore just to go back to the regular cursor rate. So the same system interrupt that flashes the cursor also reads the keyboard and also monitors the keys here and engages the motor and disengages when necessary. And it occurred to me, wouldn't it be neat if we could slow that system interrupt down? We saw it slow, like the maximum 16-bit slowness we could do, which only allowed us to go about not even quite 4 times slower than normal, right? Normally you're at 17,000, instead up to 65,000. It's about 3.8 times slower than normal. Well, the C64 CIA actually has 2 16-bit timers, and there's a way of linking those. And I wondered, is it possible to link the two together to do 32-bit slowness? It turns out it's not that difficult. So that's what this little program does. You might want to play around with this. So normally timer A is sending the interrupt that drives the whole system. So we're just going to poke that off here. I'm not going to go super in depth at this. This could be its own whole video. So what we can do is set timer A to its maximum 65,536. We can set timer B to just, in this case, 16, which is a very small amount of the potential 65,535 it could do as well. Sorry, I said 56. I meant 65535. So 16 out of 65,000 is a very small amount. But now what we can do is tell timer B to count timer A going down to 0. So timer A is going to keep going from 65535 down to 0. Every time that happens, timer B will notice and decrement its own value. And then we'll tell timer B to fire an interrupt when timer B hits 0. Essentially, we've linked timer A and B into one 32-bit counter, and now timer B is going to cause the interrupts. And it amazes me that the 64 is flexible enough. I can do just a bunch of pokes, and it will change the system interrupt. I didn't have to hack the kernel or anything like that. Okay, so let's run this program. And now you'll see how crazy slow it is. There, okay, watch the cursor. It's ready. The cursor comes on. This is a single flash of the cursor. Still waiting. Waiting for it to blink. There, it's off. Okay, and now I'm going to try fast forwarding. Did you see how there's... There. So there was a small lag there. I pressed fast forward. That was a longer leg. It's kind of just lucky because the interrupts are firing slowly in the background, and it just depends when you happen to press the key how long the lag will be. I'll do it again and listen. Did you hear how it took a little while for the motor to shut down as well? Okay, so that doesn't seem slow enough to me. So I'm going to crank this up another 16 times longer. And now I'm going to fast forward. There. So, okay, rewind. Okay, now I'm going to press stop. And the motor's still engaged. There. And the motor finally shut down. So I think it works out that if you link both timers to the maximum 32-bit value, you end up with about a 71-minute delay between interrupts. But they will happen. Oh, I should note that it takes 20 interrupts to flash the cursor. So normally we've got 60 interrupts. You've got about 3 flashes a second, or 3 inversions a second, 1.5 full flashes a second of the cursor. But within each flash, there are 20 checks of the keyboard and 20 checks for the cassette motor. So you actually have to really slow the interrupts down before it starts affecting the cassette motor. Okay, so I'm in the Super Snapshot monitor. Let's actually look at the disassembly of the kernel just for the small part here. Every 6502, so 6510, has a number of vectors at the end of memory. FFFA is where they start, and it's actually the last, here there's 3 groups of 2. FF48 is what's called the IRQ vector, and it's in high byte, low byte format. So what that means is whenever an interrupt happens, such as that triggered by the CIA, the input-output chip, it will look up here, FF48, and it will start executing code there. It will jump there. So if we disassemble it, FF48, see here the code, it pushes a bunch of stuff on the stack. It actually checks for a few things in case you had the break vector. It looks on the stack. It's a little funny how it does this. Okay, so it goes through here, and that jumps through this location, 0314. We're not going to follow every path here. This is the main path. So it's going to jump indirectly to whatever's in 0314. So if we look at location 0314, and we see again in low byte, high byte format, a vector to EA31. So we'll disassemble at EA31. And this is the main normal kernel service routine, or the system IRQ that happens. This is a bunch of cursor flashing business here. And this is what we've been looking for, starting at EA61. And as you might expect, it loads location 1. That's that control input-output port, controls the kernel and the cassette. So it gets that, ends it with a value of 10 hex, and that is just bit 4, and that is the cassette button status. And if it's equal to 0, then that means a button has been pushed, or is being pushed. Doesn't mean it's a new push, just that it is pushed. Branch if that's equal to EA71, so that would branch ahead. Okay, so if no button has been pushed, let's go through in order here. Just because the Y register is free, we're going to put 0 in there and store it in this location C0 that we haven't talked about yet. C0, according to mapping the C64, is the tape motor interlock. I didn't know anything about that either. I've got an example of that we'll look at in a moment. But basically it clears the tape interlock. Then it again checks location 1. It doesn't have the current state of location 1 anymore after that AND. So it loads it. It ORs it with 20, which is setting the motor bit. That's bit 5. It's setting the motor bit, which means turning off the motor. This branch might be confusing, but it's actually a branch always. After this OR, there's no way that the accumulator is going to be 0. It's going to be at least 20 hex, if not even more. And it branches ahead to EA79. So that was confusing at first, but that's just a branch always. Now this is where it picks up. If a cassette player button was pressed, it's going to load that tape motor interlock flag, checking what the state of it was. If it was 0, it's going to branch ahead. But if it wasn't 0, then it's going to load location 1 yet again, and it with 1F, which means preserve the low 5 bits, but clear or 0 the motor bit. That means turn on the motor. Okay? So if the interlock bit is not 0, then it will turn on the motor. If the interlock flag is not set, then it branches ahead to here, which continues on with the keyboard scan and all that sort of thing. And there was one other path here. Oh yeah, here, branch always to EA79. That's just branching here to store the state of the motor. So basically it's checking for a key press. It will turn on the motor or turn off the motor, but it's kind of moderated by this tape interlock bit. Turns out that user programs can use that to control the tape deck without interference from the kernel. So for our last example, or our last little bit here, we're going to look at that. Okay, so I think as we've established, peak 1 is 55 by default. So what if we want to turn on the cassette motor ourselves? Well, just like we saw in that, you should be able to poke 1, comma peak 1. This is what that machine language was just doing. Load the current state of 1. And if you want to turn it on, you would AND it with 31. That in binary is when you AND, you keep all these bits, but you force that one to be 0, which would turn on the motor. So let's do that. But I don't hear the motor come on. Well, if we print peak 1, we still have 55. So why didn't that work? Why can't you poke that? That's because the kernel switches the motor off immediately. Okay, now we can engage the motor by pressing the play button. Now you might think we should be able to turn off the motor with an OR 32. That's turning bit 5 on, which means motor off. But it doesn't work. Actually, it makes a very brief sound. Let's try this. 0. Oops. Well, that was funny. Ooh, got a little Swedish there. If you can see or hear that, but our program is turning off the motor and the kernel's turning it back on really quick. So we're actually just going really slow. It's like a lower pitch. If I hit stop, the pitch of it should go back up because then it's just going to stay play without my basic program fighting with the kernel. Yeah. Okay, so in either of those cases, we're finding that our basic program can't turn the motor on or off, but you might want to do that because you might load part of a program and then you want to pause the motor and then continue it again. We're just doing this from basic because it's easier. Of course, it's probably more useful in assembly language, but this video would be even longer then. So this is where that tape interlock bit comes in. So once again, we'll just want to check in on that. Now, tape interlock bit is C0 hex or 192 decimal. Actually, we're going to do a peek on that as well. You see, normally it's 0. Now, if I poke 192, 255, it could be any non-zero value. You see, it's still a 0. Well, the kernel is also clearing that automatically whenever a key isn't pressed. Okay, so the sequence here is to press play. Now you can poke 192, 255, and it will stay. You see, the kernel hasn't reset it. And now we can poke 1, peak 1, or 32. Yay! So we have stopped the motor under software control. And we can poke 1, peak 1, and 31 to zero out that 5th bit again and turn the motor back on. There. Now it's playing again. Stop. Start. And that's all because we use this tape interlock. If I put 0 back in there, it continues to play, but now it's ignoring my stop and starts. All right, so much of that was new to me, and I hope you learned something too. I don't know why it took me so long to say all that, all those examples. I hope I can cut this down. It's still going to be a really long video, I think. I hope all those various ways of looking at it help with the understanding of it. And maybe you'll find some application for it as well. Yeah, it just kind of amazes me that this was all going on. I've owned one of these for 40 years now. And I had no idea that ultimately it was the computer that was in control, not me, when I was fast forwarding, rewinding, or even pressing play, it was all up to the 64 to choose or disallow the motor to actually work. So it just goes to show that the 64 is the boss. Thank you very much to my patrons for their support. Thank you for watching, and we'll talk to you next time.